Inverted pendulum. In this exercise we have an inverted pendulum, so it is a carriage represented in green and a pendulum here. At the tip of the pendulum we have a mass mr at point B, and using the Euler Lagrange method we need to find the state equation of this system and after to simulate using a Runge-Kutta method. So first we have to understand that in our system we have 2 degrees of freedom, s and theta. So s the distance of the carriage to the origin, and theta the angle between the pendulum and the vertical. And so I build my vector q containing s and theta, and the Lagrangian is a function which depends on q and q dot. So here is my system. I recall that L is equal to the kinetic energy T, which depends on Q and Q dot, minus the potential energy V, which depends on Q. So I recall that Q is equal to S here, and theta, it is this vector. Now the kinetic energy of the system is equal to the kinetic energy of the carriage plus the kinetic energy of the rod, so which depends on Vb, the speed of the point B here, and it is given by this expression. Okay, and for the potential energy it is only the potential energy of the rod. So it corresponds to this expression where L is the length of the pendulum. So here it's A. So the Lagrangian, which is the difference between the kinetic energy and the potential energy, is given here, where here it's Q, here it is Q dot. So it corresponds to this expression. Number 2, using SimPy, write the Euler Lagrange equation. The Euler Lagrange equations are given by this. U is associated to the carriage, so to S is the force on the carriage. So this is why I have the U here. So of course, if I put all these vectors on the other side, I will obtain a function S, so this minus that, which depends on Q dot Q dot dot, so the Q dot dot occur because I differentiate with respect to T here, and also U. And we'll see that S is given by that. So in the Lagrangian approach, Q dot and Q dot dot should be considered as independent variable. So this is why I will have to destroy the differential links between Q dot and Q dot dot in a SimPy in order to make them independent. So I will show how to do this. So I will use SimPy. So SimPy, I have to create my symbol T for the time, here for my parameters, and I will create my function which depends on T. So my function will depend on T will have U. Here it will correspond to Q, the vector Q, the degrees of freedom S and theta. Here it corresponds to Q dot, and this one corresponds to Q dot dot. Okay, so I create here my Lagrangian. So first the potential energy, here the kinetic energy as explained previously, and I create here my Lagrangian. Okay. Now in the second step I will have to build some matrices so that I will be able to compute the Lagrangian. So it's a pure syntax due to SimPy. I create here my vector Q dot, and here it is my function s, which corresponds to my Euler Lagrange equation. So recall that when s equals 0, this corresponds to my Euler Lagrange equation. So I will print s, but we will see that the dependency between q dot dot and dq will appear. So I will make independent using the substitution here, as we will see. Then I will provide a simplification of the expression and print the function s. So here it is my program. I will run it. My Lagrangian L is given here. The expression S, as we have seen previously, it will make appear the derivative of S with respect to time t, and this I want to replace by S dot dot, so by this. And it is why here I use the substitution here. So I will replace this expression by ds, this one by dts, and so on. Question number 3, I have to derive the state equations of the system using SymPy as much as possible. So it means that I have to try to avoid computing all symbolic computation by myself. So recall that the Euler Lagrange equation are given by this equation, which should be equal to 0. And I will try to isolate s dot dot and theta dot dot from this expression. So first we see that s dot dot and theta dot dot, here, here, and here, appear linearly in this equation. So if I want to isolate in this expression s dot dot and theta dot dot, I will be able to do it using the Jacobian method. So I will try to explain now what it means. So I have S, which depends on Q, Q dot, Q dot dot, and U, which is equal to the derivative with respect to Q dot dot, considered as an independent variable, of S, which depends on all these quantities, multiply by Q dot dot, plus S of Q, Q dot 0 for Q dot dot, and U. Okay. And this is only due to the fact that s dot dot and theta dot dot occur linearly in the expression. This is why I have this equation. And this, I am able to compute it using SymPy, because it's just a differentiation of s with respect to q dot dot, and I will call it m. And m will depend on q and q dot. And this one I will call it b, and b depends on q, q dot, and of course not q dot dot, and u also. So I will compute them using SymPy. And then once I have this, I will have, since all should be equal to 0, I will be able to isolate q dot dot. So q dot dot will be equal to m minus 1, okay, of q dot, minus, here, multiply by b of q dot and u. So I have this expression, and from this expression I will have the state equation, which give me q dot equal q dot, and q dot dot, which is equal to this expression, minus m minus 1, and so on. So here I will have something which corresponds to x dot. This will correspond to f of x and u. And x will be the state vector which contains q and q dot. So we should understand that the q dot here is a component of x dot, whereas this q dot dot here is a component of x. So for this, this is the final expression. To do this, I will use SymPy for this. So I will compute M as a Jacobian as described above with respect to d dq. Here b the same, and I replace q dot dot by 0. Then I will compute this, which corresponds to this, and I will simplify the two expressions, and I will print them, and I will see that I obtain that. Then I will be able to get my state equation using this, and this corresponds to a copy of this, and I have renamed x is equal to q dot. Okay. I take SymPy here. I will run the expression. I compute my Lagrangian, and I obtain the expression I have just shown few seconds before. Question number 4. Propose a simulation using a Runge-Kutta method. We have here an expression of q dot dot with respect to q and q dot, and from this we should obtain, using SymPy, a formulation where I have x dot, which is a function of f and ux x and u, so that I can use a Runge-Kutta method. So for this, since I have an expression of q dot with respect to q and q dot, it means that I am able to express s dot dot and theta dot dot with respect to s, theta, ds, and theta dot, and the parameters also. So to obtain a Python function, I choose lambdify this expression to obtain a Python function. And from this, I should be able to build this one. So how I do this? First, I take the x as an input of f, and I will generate my variable s, theta, s dot, and theta dot. Thanks to f lambda, this one, I will be able to have the x dot here directly, and then I will return x dot. Okay, so I will return f of x and u, this one. I need a function to draw the inverted pendulum. So for this, I have an input x, and I will draw the box for the carriage, and also this for the pendulum. For the simulation, I initialize my parameters and the initial value for the state vector. Here it is the sampling time, my figure, my loop, and here the Runge-Kutta method. So from f, I am able to compute x at time t plus dt. So if I know x at time t. So let me run this. I generate here f lambda, and we can see here the simulation of the inverted pendulum using the Runge-Kutta method.